For some scalar thetas and some particular models, we may be lucky enough to find a conjugate prior that would result in a closed form posterior distribution. However, Bayesian computation can become quite difficult when theta is a vector, so there's more than one unknown parameter, and when there is no conjugate family that can be identified. So let's consider the general problem of finding the posterior expectation of g theta, which can be denoted by the expectation of g theta under the posterior distribution, so theta given x. By definition, this is equal to the integral of g theta times the posterior density, and that is equal to the integral of g theta times, that's our posterior density. So that's the likelihood times the prior divided by the marginal distribution of the x's. You can see that directly computing this integral is usually a nightmare. One thing you might be wondering about is, in this case, what can we do if we want to estimate the posterior expectation of g theta? So let's say, what if we want to estimate the posterior mean? In that case, g is just the identity function, so g theta equals theta. Well, we learned previously how to do Monte Carlo integrations. So if we know how to sample from the posterior distribution f theta given x, then we can draw a bunch of theta samples from this particular posterior distribution, and then we can use Monte Carlo integration to approximate the expectation of g theta we're interested in. And that approximation is given by g bar of theta. The problem here is that often we don't even know how to directly sample from the posterior distribution. Recall that the posterior distribution takes this form. And a lot of the times, there is no closed form solution to this density. Our question is, can we draw samples from the posterior distribution? Well, that's where MCMC methods come in handy. Markov chain Monte Carlo methods provides a workaround to the problem of sampling from the posterior distribution. Instead of directly sampling the thetas from the posterior distribution, what we can do is to set up a discrete time Markov chain, theta 1, theta 2, theta 3, etc., where the 1 to 3s indicate time points, so that the stationary distribution of this Markov chain, so the theta j's, is going to converge, or it's going to be the posterior distribution. So as the j gets large enough, as we go long enough in time, it's going to be getting close to the posterior distribution. So you can see that there might be some terminologies that you're not very familiar with. So what is a discrete time Markov chain? And what is the stationary distribution of the Markov chain? Now is a good time to switch gear to discrete time Markov chains.